Let's review first the rules. Remember, we talked about first rules of implication, modus ponens, modus tollens, pure hypothetical syllogism, disjunctive syllogism, constructive dilemma, simplification, conjunction, and addition. This is kind of all, in a sense, common sense, because this one's, it's not so much even when you learn it, but when you understand it, you don't need to even remember every single one, because the principle is more important than this writing it down, right? If you understand the principle will always tell you what you may and may not do. And of course, there's not nothing crazy. In fact, they all can be more or less reduced to just modus ponens. But that's a little bit more complicated to understand how each one of them reduces to modus ponens. Nonetheless, they can. The principle everywhere is very similar. Okay, now the rules of replacement, which we learned last time, they're not as obvious, maybe, but some of them are. Like this is very obvious. Commutativity, yeah. If you have disjunction and conjunction, you can just switch them around. That is rather common sense. Distribution is also nothing difficult. Here, well, associativity, nothing difficult. Distribution maybe a little bit, but it is just the idea of how do you distribute. Double negation, super easy. It is so much common sense that, like I said, some of you are already trying to use it before. But technically, before we actually covered it, it's not an allowable rule. So this is what we done last time. Okay, now we will add few more rules of replacement, and they also are very useful, and it's important to understand. Transposition. So what happens in transposition? It is basically, again, related to conditional statements. You see them again and again, those conditional statements, which is why we started with them at the very beginning. It's basically saying that if you switch around your antecedent and consequent, you just need to change their signs, right? So that's pretty much all that transposition tells you. If you switch them, you can switch them, but then you just need to change their signs. They have to become opposite of what they were. Remember, it's not necessarily negative, because if they were negative to begin with, they'll become positive, but the sign should be changed to the opposite. Then material implication. This is an interesting one. It also starts with the conditional statement, if P then Q. But then what we can do here is to change it for disjunction. And it seems like, how can we change it for disjunction? Well, yes, we can. If we just negate our antecedent. And that's pretty much the only thing we need to do. We negate our antecedent, and then from if P then Q, it could become not P or Q. If you think about it, there's like language to go along with it. Instead of saying, if you bother me, then I'll punch you in the nose. This is the book example. A little violent, but if you bother me, then I'll punch you in the nose. You can say, either you stop bothering me, or I'll punch you in the nose. Right. And it would mean exactly the same thing, right? So that just gives you these two choices. Since P is a sufficient condition, well, then the only two options becomes either the sufficient is not satisfied or the consequent will follow. Then material equivalence. A material equivalence is just basically common sense based on what we already learned before. Let's see if you can understand it. So if you have, remember that P triple bar Q just basically is two conditional statements going both ways, right? If P then Q and then Q, if Q then P. So this is just spelled out in this case. They're spelling it out. If P then Q and if Q then P. We, I think, already mentioned it. Slightly different way to think about it is like this. If you have this, if P then Q, remember, they can only both be, the whole thing can be only true if they either both false or both true. And from that, it does actually follows that it is indeed equivalent to P and Q, or, so that would be one condition for them, both of them being true, right? If P and Q is true and both of them are true. Following? You're too busy writing it down. So remember, if both of them are true, the whole thing will be true, right? So that's one situation. Or you can have another situation, not P and not Q, which also would make it true. That's in a situation when both of them are false. So then if you flip the sign, they both become true. And so the whole thing is again true. So you can either have this or you can have this. In both cases, you will get true for the whole statement. So we just basically breaks it down. But then writing proofs, that could be very useful sometimes, because if you have P triple bar Q, you may need for your conclusion, for example, P and Q. Then you can do this, and you can work with this formula and pull out P and Q instead. Exportation. Now exportation is a little bit more complicated, but hopefully not too complicated. So P and Q, therefore R, that whole thing is equivalent to if P, then if Q, then R. It's basically this one breaks down. If we have both P and Q, then we have R. And it is equivalent to if we have P, then we have Q, and then we have R. Another language example. If Bob and Sue told the truth, then Jim is guilty. Right? So that would be if Bob and Sue told the truth, then Jim is guilty. That is equivalent to if Bob told the truth, then if Sue told the truth, then Jim is guilty. Tautology. Well, that is another easy one. That basically means that if you have any letter, in this case P, that also is equivalent to P or P, and P and P. Could be useful sometimes for the purposes of proofs. Of course, it is a tautology, because obviously if you have P, it's equivalent to P or P. It is so obvious that it is indeed almost the definition of tautology. And similarly, if you have P, it is equivalent to P and P. So let's see how we can use this in a proof. This is rather simple. One premise argument. Right? So let's look at it. One premise is not A, and our conclusion is if A, then B. So first we can add B to our A here, which is our replication we learned before, not A or B. That is allowed. But now we can do the implication here from 2 and get if A, then material implication. So if we go back, that's what we are using, right? If P then Q, so if A then D, we can replace it with not A or D. So that's basically this line. So that then becomes if A then D. They are equivalent. Another example using implication and double negation. So in this case we're starting with if F then G, F or G, and the conclusion should just be G. Well, to follow the rules more strictly, we can just add double negation to F, which is the same thing as F. So this is in order for us to remove one of these negations and turn it into if F then G by implication. So then we can proceed adding double negation to G using transposition, not G, therefore F. So we are switching them around and changing signs. So this one had double negation, now it has single negation. This one had negation, now it has no negation. Right? Then we can use pure hypothetical syllogism for 1 and 6. 1 is if F then G, 6 is if not G then F. So we're starting with this one, then this one, but they actually, that's another question somebody got on the exam. I think somebody got a problem on the exam because they were doing 6, 1. Not 6, 1, there are the numbers, but out of sequence, right? And again, software for whatever reason does not allow that. Even though it seems like that's not a big difference. But you have to still go sequentially from lower number to the higher number, even though they're pure hypothetical here, strictly speaking, is 6, 1, not 1, 6. Right? They're using first 6, then 1. But order of premises doesn't really matter, and when you write it here, they do want you to go from lower number to the higher number. So then if you do that, you get if not G, then G. Then you can again use implication on that and replace it with negation of G or G. And since now it became double negation of G, then it's G or G, which is tautology. So you just go backwards from tautology. If it's G or G, then obviously it is G. So that is this proof now using new rules. Just make sure you understand everything. Okay, so another example. We have this kind of argument. So let's see what the proof for it is. Okay. The conclusion can be obtained by rearranging the components of the single premise. This is how you can do it. So line 1, you are using exposition, and you basically just going kind of backwards again from right to left. J and K, therefore L. So this is indeed equivalent to this. Now, you want your K on the left side, so you use commutativity. That's very easy. You just switch them around. But from that, using again exposition, you can now get with K then with J then L. You see, once you use these two operations, we can reach the solution again. Another example. So if M then N, if M then O, and the solution is, conclusion is if M then N and O. We need to find something to link the premises together in this type of a solution. Hypothetical will not work. So what can we do? Let's see. First, we can use the implication to switch it to disjunction. Right? We take in 1 and change it to disjunction. We take in 2 and also change it to disjunction. So now we have these two disjunction, which we can connect because, remember, if they are on separate lines, we can use the conjunction of both lines. Once we did that, we can use distribution now. Using distribution, we are pulling not M out of this whole thing. So not M or N and O, which already is practically this, except that we need, again, material implication to replace the disjunction with the horseshoe by changing the sign of our antecedent. Let's see another example. Let's say we have something like this. Now that is a longer argument with 4 lines. And in the end, we're supposed to get the triple bar, if and only if. The conclusion is biconditional. So we need at some point get if P then R, if R then P, because that's basically what it is, right? So remember, it would be equivalent to if P then. So as long as we get that from here, that would be what we need. Hypothetical syllogism, of course, could work. Premises 1 and 3 can be used to set up hypothetical syllogism. Premises 2 and 4 provide the other one. Because this is the first one, right? This is the other one. So 1 and 3 do allow us to do that for the left side, and 2 and 4 for the right side. But how are we going to do that? So we will start with transposition for the line 3. And that would give us, if Q then R, removing those negations. And then that can be used as pure hypothetical. Lines 1 and 5 together give us if P then R. That's already one side which we need, the left side, right? The right side, we can use exposition on line 4, and that will give us S and T, therefore P. And again, pure hypothetical 2 and 7 will give us then if R then P, which is the other side. So now it's easy. Once we gotten them by themselves, on this one on one line, this one on the other line, we can just conjunct them, and there we go. That would be equivalent to triple bar. Another example, as we saw in 7.3, if it's not readily apparent how the conclusion can be derived, we can use the rules of replacement to deconstruct the conclusion. So here we're going at the conclusion and trying to deconstruct it. And then we'll hopefully see how we can get there. So let's see how we can deconstruct the conclusion. Exposition first will give us not R and not M, therefore K. De Morgan's rule, right? We are pulling out this negation, replacing conjunction with disjunction, and then another transposition. If K, then in this case we need two negations, because we already have one, R and M, but two negations that can be removed. So then we get not K, therefore if R then M. And if we get this, you can hopefully see that we already have this chunk and we have this chunk. So we just need to get to them. How are we going to get to them? Well, this is the complete solution. So first, we're doing the transposition on line 1. Not K, therefore not S, which is equivalent to not K, therefore S. Your hypothetical syllogism 2 and 4, which gives us if not K, then R or M, which actually is already our conclusion, right? We already know it's our conclusion. That's what we got there. We just need to kind of work backwards towards it. So we're using transposition on 5, then removing the double negation, then that negation, again, it's kind of like reverse of what we did on the previous, right? We are distributing these negations back here, and once we distributed them, exposition. So that whole thing here is the reverse of what we saw in the previous one. But once we got here, we know that this reverse will lead us to the correct proof. Another example. There's a lot of examples, but I mean, that's really the only way to go through it right now, other than exercises. We'll do more exercises in the end, but if you follow along through examples, that can hopefully explain some of these things. So we've K then M, L then M, and this is our solution. Deconstructing the conclusion, the formula of premises suggests that we use some procedure which will combine M separately with K and L. This in turn suggests distribution. But before we can use distribution, we must eliminate the horseshoe via material implication. So this is the deconstruction of the conclusion. Fairly long one here. So starting with implication, we're just turning it into a disjunction. Morgan's rule, we are sticking this negation inside the parentheses, and we can flip them around with commutativity to the distribution of this M here and here, then another commutativity and another commutativity, just sweeping both sides, and then implication and another implication will finally get us where we need to get. And that, if you look here, that suggests how this can be resolved, because we already have these chunks, right? So then that's already pretty much our premises here. And since it is our premises and they are in the conclusion, we can just basically start with combining them, and that is what we got on the previous line, right? This conjunction of these two. And then just work backwards, exactly what we did on deconstruction. So first implication here again, then switching this side, switching the other side, then distribution, then commutativity. Then so basically once we deconstructed our conclusion, we know the order which we will need later on. The deconstruction led us to our premises, and that tells us in what order we can, if we combine them, just go backwards to our conclusion. Okay, so just some of the strategies. Material implication can be used to set up hypothetical syllogism. So if we have premises like this, right, you remember that each one of them through implication can be turned into if A then B, if B then C, and that is already pure hypothetical syllogism, so then we can get if A then C. So that's one of the strategies which can be useful, depending on what your premises are. Exportation can be used to set up modus ponens. If we have this and this, that doesn't look like modus ponens yet, but remember that using exportation, that can be turned into this. And now you can obviously immediately see whether this modus ponens given us is B then C. Can be used also to set up modus tollens. Let's say if we have a negation of C here, then exportation can give us this, and that will in turn, because we have not C, give us a negation of our antecedent. Addition can be used to set up material implication. So if we get A or B, we add not B here, then we switch not B to the left side, and that is equivalent to if B then A. So you see we got from A to if B then A. How? We just added not B. Disjunction with not B. Interesting trick to use. Transposition can be used to set up hypothetical syllogism as well. So if we have these two premises and then on 2 we can use transposition, switch them around, remove the negations, and immediately get the pure hypothetical syllogism. Transposition for constructive dilemma, if A then B and if C then D, not B or not D. So that can we use transposition on number 1, and we do get our not B and not and C here, but one more transposition. So both sides transposed do give us the not B and not D, and that can give us not A and not C. Constructive dilemma can be set up, can be used to set up tautology. So we have the constructive dilemma with these two. Now, it does give us C or C, but C or C is equivalent to just C. If they are the same, if our consequences are the same there. Material implication can also be used to set up tautology. So if we have if A done not A somewhere, we can replace it not A or not A, equivalent to just not A. Can be used to set up distribution. Well, I guess you can go through these rules on your own later on too. Otherwise, I'm afraid you'll get too bored if I continue with all of them.